Let's continue with our discussion on suspended growth reactor. We have looked at the mass balance for the simple setup. One aerobic CSTR treating a single soluble organic substrate using a single type of biomass. In this class, we will extend the model beyond that because in real life, in addition to just soluble substrate, the influent may contain a wide variety of contents such as inert particulate or soluble matter, biomass, and debris. The presence of soluble, non-biodegradable organic matter in the influent has no impact on the biological processes or mass balances, although the soluble, non-biodegradable organic matter can be volatile and or be absorbable in certain treatment processes. As for the inert particles, although they do not participate in any bioreactions either, their accumulation in the reactor can change the total solids concentration and active fraction of biomass. First, we can find the steady-state concentration of the inert particles from this mass balance. Influent solid mass equals to the effluent solid mass. Because F over Fw equals to SRT over HRT, the inert particle concentration in the reactor equals to the inert particle concentration in the influent times the SRT divided by HRT. Because the solids are recycled, SRT is larger than HRT. Therefore, the inert solid concentration in the reactor is larger than that in the influent. We define the combination of active biomass, debris, and inert particles as mixed liquor suspended solids, MLSS, as they are all separated from the liquid and or recycled by the biomass separator or clarifier. We can write the expression for MLSS from previously defined descriptions. MLSS is an important and widely used parameter for biological wastewater treatment, as it's what's actually measured in real-life reactors. Now, the inert particles in the reactor also becomes the denominator for the active fraction. So the active fraction is active biomass divided by MLSS, and is lower than that with no inert particles in the influent. Because the inert particles are removed by biomass separator or the clarifier, the expression for the biomass wastage rate should also include inert particles. So the wastage rate should be the previously expressed wastage rate or excess biomass production rate without inert particles, plus the inert particle concentration in the reactor times the wasting flow rate. Because there's no reaction of the inert particles, all influent inert particles are wasted. So the wastage rate also equals to excess biomass production rate without inert particles plus influent flow rate times influent inert particle concentration. In addition to non-biodegradable materials, there can be biomass in the influent as growth can occur before the bioreactor, such as in the wastewater collection system, headworks, and in the primary clarifier. The influent biomass is denoted by XBHTO. Can you pause this video to write the steady-state biomass mass balance, including the biomass in the influent? Okay, influent biomass in COD minus wasted biomass in COD plus reaction equals to 0. We can divide both sides by active biomass concentration XBHT and transform the mass balance to this. Compared to no biomass in influent, the specific growth rate is lower with the presence of biomass in the influent. In other words, because there's biomass in the influent, the biomass in the reactor do not have to grow as fast to maintain itself. We can substitute this expression for specific growth rate, μh, in the expression for active biomass concentration deducted from the soluble substrate mass balance. And that can be substituted in the expression for debris, which is deducted from debris biomass. If there's debris in influent, it can be regarded as inert particles and does not participate in any reactions. Therefore, the influent debris term xdTO can be directly added in the equation with a factor of SRT over HRT, as it is removed in the waste stream. The MLSS represented by XMT includes the active biomass and debris generated in the reactor, the active biomass and debris in the influent, and the inert particle in the influent. Then we can divide the active biomass concentration by MLSS to get the active fraction. And the wastage rate, which is MLSS times wastage flow rate, or MLSS times influent flow rate times HRT divided by SRT. We can also connect the expression for specific growth rate, μh, with the Monod equation to find the expression for the soluble substrate concentration, SS. Recall that when the SRT is infinitely long, the effluent substrate concentration is the lowest possible value that can be achieved with this reactor configuration. Compared to no biomass in influent, a lower minimum S sub S can be achieved with biomass in the influent. Let omega be the ratio of minimum soluble substrate concentration with biomass in the influent to that without biomass in the influent. Because in most cases, the specific decay rate is much lower than the specific growth rate. So 1 minus BH over mu max roughly equals to 1. We can simplify the omega expression to this. The more biomass in the influent, the lower SS min can be achieved. Again, from the mass balance of active biomass and Monod equation, we can get this equation. And we can substitute the expression for active biomass in this equation. After simplification, we can get an expression for soluble substrate with influent biomass concentration, influent soluble substrate concentration, half saturation coefficient, and yield. For the oxygen demand, we can write the reaction rate from the stoichiometry and kinetics matrix. Substituting the expression for active biomass and specific growth rate with active biomass in influent, we can get the expression for oxygen requirement with biomass in influent. Compared to the oxygen requirement with no biomass in influent, the oxygen requirement increases with active biomass in influent. This also corroborates with lower minimum substrate concentration, or SS min, in the effluent. There might also be biodegradable solids pass through the headworks and primary clarifier and enters the bioreactor. They cannot be directly utilized by biomass as substrate, as they are too large to pass through the cell membrane. Before being utilized, they are first hydrolyzed to soluble substrates by extracellular enzymes. In the model, this is an independent process besides the cell growth and decay. It is included in the activated sludge model 1. Remember that we have covered the basics of hydrolysis process. There's no electron transfer or COD reduction, and the kinetics is either first order or Monod type equation.